Hi, Dung-Hai.
Hi, sorry, I was muted.
Yeah. Welcome, Dung-Hai.
Thank you. Should I test the sharing?
Yeah. You can share now.
Yes.
Okay.
Your co-host now. 欢迎。
You will stop others. Okay.
Yes.
Share. Then. Wait. How do I minimize this?
Maybe this escape.
Oh.
ESC escape. If you are using the full screen right now. Actually, usually, you can select the
Yeah. Anyway, I think it works now. Yeah.
You can select the program the software you want to show. For example, PowerPoint here. Right? You just need to you can select that you only want to share the PowerPoint, not the full desktop.
Yeah.
You don't need to share the full screen. There's a mode you can select when you.
I see. This works. Yeah.
Yeah. I guess I don't mind for you guys to see the rest of my screen.
I think you can just go to full screen now. Then it works. Right. This is not the correct mode. I think this is your.
Huh?
This is the presenter mode, so I can see the.
Oh, I see. You don't see the full screen here?
No, I think I see your mode. Yeah, you should change the mode.
Wait, hold on 1 second. How do I change the mode?
Maybe in display setting.
No, sorry. Let me disconnect my monitor and see what happened. Is this okay?
That works. Yeah, it's perfect.
Okay.
No, it's good.
Laser pointer. Okay.
Yeah, it works.
All right. Okay. All right. So I will just leave this page here.
You can.
You can do whatever you want. We are still very early, so I think
if you want to
still have 15 minutes. So
right. I will go do something else, and I leave this page there.
Yeah, sure.
This one.
Okay. Thank you.
See you later.
Yeah. See you.
Dung-Hai.
Hey, yeah.
Yeah, so we'll wait for another few minutes, like 3 minutes, because
Okay.
people are usually coming late.
Okay.
Joey, maybe we can start now.
Okay.
Yeah. Dung-Hai, are you ready?
Yeah.
Okay. Hello, everyone. Welcome. Today it's our great pleasure to have Professor Dung-Hai Lee as our speaker for the CMSA seminar on HTC. So Dung-Hai, as many of you know, is a professor in University of California, Berkeley. He is famous for many works in strongly correlated systems, such as in quantum Hall, in HTC cuprate, in iron superconductor, and more recently, also in symmetry protected topological phases and its phase transition. So today, Dung-Hai will tell us about his recent work on non-abelian bosonization in higher dimensions. Let's welcome Dung-Hai. Dung-Hai, please.
Thank you. Thank you. Can you hear me all right?
Yes, yes.
Okay, right. Thank you for the opportunity to speak here. The title of my talk is non-abelian bosonization in 2 and 3 space dimensions and the applications. The applications I will include I will include 3 subjects if time allow. The first one is SU2 gauge theory of the pi flux phase of the half-field Hubbard model. And the second topic is the critical spin liquid in 1, 2, 3 dimensions. And the last one is the twisted bilayer graphene. The content of this talk is in this archive paper. During the whole research, the heavy weightlifting is performed by Yanta Huang, who is a student in my group, and he has finished up now. Okay. So at the start, I would like to spell out the limitation on our work. Our result only applies to fermions with relativistic dispersion. So for example, semi-metal with a Fermi level intersecting the Dirac point is within the scope of this work. But the metals where the Fermi energy intersect a Fermi surface is not within the scope of this work. It is then important to ask how relevant are the massless relativistic fermion theories in condensed matter physics. Recently, in condensed matter physics, the 2+1d and the 3+1d, d means a space-time, massless relativistic fermions have been realized in important systems. Just give a few examples. Graphene, twisted bilayer graphene, Dirac, and the Weyl semi-metal, etc. But moreover, massless relativistic fermion can also appear as the mean field theory of some strongly correlated problem. And this mean field theory set the starting point for further more involved treatment. And the example here is the pi flux phase of Hubbard model at half filling. Another place where massless relativistic fermion appear is on the boundary of topological insulators and the superconductors. In this talk, I will this research benefit a lot from the insight we learn from topological insulators and the superconductors. Okay, so here is the outline of my talk. I will start with a background which set the stage for our research. And after that, I will present the main idea. Okay. And when I discuss the main idea, I will not give the glorious detail. Okay. Then I will go directly to present the bosonization result. Okay. Now, after the bosonization result, I'm going to talk about the applications. If after the applications, they are still time, I would like to go back and present more layer of the details of the bosonization. So that's my plan. Okay. Right. Okay, so let's start with the background. Bosonization in 1+1d has been a very useful theoretical tool. I just went to Google Scholar and did a quick search. There's about 18,000 papers using the bosonization. And the best known version of bosonization is the abelian bosonization in 1+1 dimension. And those are started with these 3 papers. Okay. Strange. I have trouble going to the next picture. Okay. So for example, let's talk about massless spinless fermion with non-relativistic dispersion. We are all familiar with that. If we are interested in low energy, namely particle hole excitation near the Fermi energy, then we linearize the dispersion around the Fermi point. And that gives rise to a relativistic effective Hamiltonian. Here, this Z is the shorthand for Pauli matrix sigma Z. And this Hamiltonian has a right mover, which corresponding to Z equal to +1, and a left mover, which corresponding to Z equal to -1. Upon bosonization, the particle hole excitation is described by a free Gaussian theory. Here, pi is the canonical conjugate field of phi. So this is a scalar boson field theory, harmonic oscillator-like. And in this theory, the fermions are solitons in the boson field phi. Okay, but what about the case that the fermion has flavor for fermions? So in this case, we have a n-flavored fermion, and here Z in stand for the tensor product of sigma Z and the identity n by n matrix. Again, the fermion has a right mover and the left mover. There's something wrong. Okay, so it is quite straightforward to show that this free fermion Hamiltonian has the following symmetry, namely the charge conjugation symmetry, where psi are sent to psi daggers. It has time reversal symmetry, which is anti-unitary. In addition to this fermion transformation, we have I goes to -I upon time reversal. And then it also has the chiral UN cross UN symmetry, where I transform the right moving and the left moving fermions by different UN matrices. Okay, the last symmetry is emergent, and it has anomalies, as we shall see pretty soon. Okay. Now, facing a fermion theory which has so many internal flavor, degree of freedom, and symmetry, it is desirable to have a boson theory which explicitly exhibit these internal symmetries. Right? So this was achieved.
Excuse me, Dung-Hai.
Yes.
You choose a time reversal, which is t squared +1.
Yeah. So
t squared
yeah. Let me clarify on that. Let me go back.
-1 fermion parity, of course.
Yeah. So So first of all, the time reversal transformation is not unique. You can compound any time reversal anti-unitary transformation you use with the unitary transformation in the problem. So it's quite easy for me to combine the time reversal transformation with the unitary transformation to create a t² equal to -1. Okay, the reason I choose this particular t, okay, is not for no reason. The way we choose the time reversal transformation, okay, is such that after the maximum continuous group, after the anomaly-free portion of the maximum continuous group is gauged, the time reversal is not broken in 1+1 and 3+1 dimension. Okay, that's the choice dictate our choosing of time reversal. Is that okay?
Okay.
Okay, so this was a boson theory which reflect all the internal symmetry was achieved in Witten's non-abelian bosonization work, where he showed that the bosonized version of an n-flavor massless Dirac fermion is this theory. In fact, in his original paper, he was dealing with two n-flavor Majorana fermion, but a simple translation is for the n-flavor Dirac fermion is that this is the bosonized theory. Now, because not all of the audience are familiar with the language of Wess-Zumino-Witten sigma model, so let me present a toy version to better understand the notation in this equation. Let me consider the simplest example of the Wess-Zumino-Witten theory. And this is a 0+1 dimensional Wess-Zumino-Witten theory associated with the coherent state path integral of a single spin. Okay. It's quite well known that such a path integral is equivalent to the Feynman path integral of a charged particle running on the unit sphere and subjected to the magnetic field of a magnetic monopole. Okay, so here the first term can be called a stiffness term, or it can be called a kinetic energy if you view the Feynman path integral. And the second term is the J dot A Aharonov bone phase term. The monopole is defined to have strength 2s. S is the spin. Okay. Now we can, in the language that I shall use in the rest of the talk, this n hat, okay, which is a unit vector, is called the order parameter, and the space where n hat lives in is called the order parameter manifold, abbreviated as OPM. Okay. Now we can use the familiar Stokes theorem to convert the line integral in the Aharonov bone phase into a surface integral. Here we choose to integrate against this cap. Okay, and this converted two-dimensional integral is the Wess-Zumino-Witten term, and here this d, this means d wedge d, so this is a two form. Okay. Now n hat twiddle is the extension of n hat into the cap. Okay, And in order for such an extension to exist, that pi1 of S2 has to be 0. S2, again, is the order parameter manifold. Pi1 is the trajectory of the order parameter. It's the 0+1 dimension space-time of the order parameter, okay? Now, right, and in order for the phase factor associated with the Wess-Zumino-Witten term to be independent of which cap, either this surface or this surface, they are both bounded by the loop. In order for the phase factor to be independent of which cap we use, we need pi2 S2. S2 is again the order parameter manifold. Pi2 is the extend a space-time. So basically, what you are doing is that you compare the Aharonov bone phase by using this cap or using this cap, and the ratio of them can be viewed as the integral over the whole S2. So if pi2 S2 is integer, then when the monopole strength is an integer, the Wess-Zumino-Witten phase factor is independent of the extension. So therefore, in this simple problem, we realize that in constructing the Wess-Zumino-Witten theory, homotopy groups is very helpful. Okay. Right. Then, yes.
Oh yeah. For the requirement on pi1, I think when you say it's required for the extension to exist, I think you mean you want the extension to be the extension of n hat tilde to be something like a constant.
Right. So look at the space-time trajectory here. If I extend it into the cap, the space-time trajectory will shrink to a point. Yeah. So that will require that the pi1 of this n hat twiddle, to be equal to 0 at that time. Mm-hmm. Right. Okay. So the quantization of the Wess-Zumino-Witten coefficient, or that 2s is equal to n spin is integer times 1/2. This is the quantization condition imposed by requiring the phase factor of the Wess-Zumino-Witten term to be independent of the extension, and this n is called level. So when we hear people say, all right, this is a level 3 Wess-Zumino-Witten term, that means this n is equal to 3. Okay. Throughout this talk, the Wess-Zumino-Witten term we shall encounter which is the result of a fermion integration, are all n equal to 1. So it's all level 1 Wess-Zumino-Witten term. Okay, so now we are ready to go back and look at Witten's result again. So for n flavor massless Dirac fermions, this is a boson theory. The first term, so the space-time now is okay. So the space-time now, unlike in the toy problem, the space-time is just S1. It's just a time circle. The space-time now is 1 + 1 is S2, and the extended space-time is a 3 disk. It's D3. So in other words, it's the solid ball. So the surface is the space-time S2, and the extended manifold is the solid ball. The first term is the generalization of the kinetic energy term or the stiffness term. And the second term is the Wess-Zumino-Witten term. And here it is a 3 form. Okay, it is a 3 form. So note that this stiffness coefficient is fixed in this bosonization. Yeah, so the analog of the order parameter n hat in the previous slide become QC. QC is a n by n unitary matrix. Okay, so the order parameter is a matrix. Okay. And the analog of n hat twiddle is QC twiddle, which is the extension of QC into the extension manifold B. Okay. And the order parameter manifold in the previous toy problem was S2. And the order parameter manifold of this problem is the group manifold of UN. It's the topological space formed by all n by n unitary matrices. And again, in order for the extension to exist, I need pi 2. Pi 2 now is the 2 is now the space-time dimension. Previously, I required pi 1 because 1 was the space-time dimension. So pi 2 of the order parameter manifold equal to 0 means that the extension exists. And finally, when pi 3, this is d plus 1. Okay, if pi 3 of the order parameter manifold is z, then the coefficient, when the coefficient is quantized of the Wess-Zumino-Witten term is quantized, the phase factor is independent of the extension. In fact, those homotopy group condition will turn out to impose some restriction on what's the smallest value of n. For one dimension, okay, with a complex Dirac fermion, n has to be greater or equal to 2. Okay, that's just for the stability of the homotopy group. Okay. Right.
Maybe another question.
Yes.
So suppose pi 3 of OPM is Z. Is it guaranteed that there's a closed 3 form on OPM?
Okay, that's a good question. So pi 3 of OPM is Z means that there exists a topological invariant, okay, where you can write down that topological invariant is the invariant that measure the pi 3 OPM. So to make sure that the Wess-Zumino-Witten term actually exists, we need to do explicit fermion integration. And when we compare the fermion integration result with the topological invariant, if the difference is only 2 pi I, then that's level 1. Okay.
But generically, I can just ask this question when I know the OPM without referring to the fermions.
Right. So pi 3 OPM is Z is a suggestive. It does not definitively say that the upon fermion integration, the Wess-Zumino-Witten term will exist.
Mm-hmm. Okay.
Right. So finally, as I said, the this coefficient 2 pi I over 24 pi square, it turns out that 1 over 24 pi square times this integral is mathematically the topological invariant of pi 3 OPM. And here, the Wess-Zumino-Witten term is just 2 pi I times the topological invariant. For that reason, this is k equal to 1. If it is 4 pi I times this topological invariant, then the level k is equal to 2. Okay. Right. So at least we understand the languages in the Witten's result. Okay. So now let me spell out the purpose of this talk. Our purpose is to bosonize the following two classes of massless fermion theories in 2+1 and 3+1d. We also bosonize 1+1, but the bosonization result in 1+1 is known. Okay, so we look at the two classes of massless fermion theory. The first is the complex class, where this psi here is a complex fermion operator. Okay, it's a Dirac fermion operator. And throughout this talk, the capital D always means spatial dimension +1. So it's the space-time dimension. Okay. In this class of the theory, a designated U1 symmetry must be respected by all mass terms introduced in the bosonization. As I shall talk pretty soon, that in bosonization, we need to introduce the mass term and then fluctuate the mass term to restore the symmetry. So for this complex class, there's a special designated U1 symmetry, which must be respected by all the mass terms. This is the complex class. And then the real class here, chi is the Majorana fermion operator. And for this class, there's no restriction. There's no designated U1 symmetry. And here, the gamma here are just the d-dimensional Dirac matrices. Of course, in the case of Majorana, this need to be d-dimensional real Dirac matrices. Or tensor IN. Again, IN is the identity matrix in the flavor space. Okay. All right. Okay. So now let me come to the main idea. Okay. The main idea is the following. We look at the problem at hand from two different points of view. The first point of view is the low energy effective theory point of view, which we view the massless fermion theory as the low energy effective theory with emerging symmetry. Emerging symmetry means a symmetry which only appear at low energy. And the emerging symmetry has anomaly. So this is the first point of view. The second point of view is to view the massless fermions as the boundary mode of topological insulator or superconductor, where all the symmetry are exact. By that, I mean the topological insulator or superconductor, which has all the emerging symmetry as the protection symmetry, okay, where all the symmetry are exact. Okay, so let us start from the low energy effective theory point of view. So to illustrate the idea, I choose to use the 1+1.
Sorry, are you fermions massless or massive?
Massless. So far, it is massless.
Massless. So the theory is scale invariant.
Yes.
But then what does it mean to discuss a low energy effective theory? Low energy relative to what?
Well, low energy relative to regularization.
But the theory is scale invariant. You don't need any regularization.
It's only in this form.
Theory.
No, this theory is a scale invariant when it is in the Dirac form. But if I add a regularization mass, it is not scale invariant.
But this theory, as it stands, we can regularize it, and then we can remove the cutoff, and we are done. And this theory is completely meaningful.
What do you mean by removing the cutoff?
Sending it to infinity. This theory, as it stands, in fact, does not even need regularization. You can compute everything without ever introducing a cutoff.
Right. I agree with that. Yeah, but okay, so I will discuss the regularization shortly. Okay.
Okay, I'll wait till you discuss.
Yeah, tell me if you still has trouble with the notion. Okay.
I think maybe Dung-Hai is thinking about this effective field, low energy field theory, some band theory, for example.
Yeah.
Right.
Yeah.
And these are just near the Dirac points.
Yeah. Yeah, that's right. Okay, so for illustration purpose, we use the 1+1d complex class, the simplest 1+1d complex class, and n equal to 1 as the example. Okay, where the Hamiltonian is given as such. Again, z stands for sigma z, +1 is the right mover, and left one is the left mover. So it's trivial to show, it's very simple to show that this Hamiltonian has a charge conjugation symmetry, time reversal symmetry, and also the chiral U1 times U1 symmetry, where I perform a U1 transformation on the right mover differently from a U1 transformation on the left mover. And this symmetry will end up to be emergent. Okay, so first of all, a very straightforward statement that is under the condition that all those symmetry, charge conjugation, time reversal, and U1 cross U1 are respected, then there's no mass term which can gap out the fermions. Okay, that's just a simple statement, namely all those symmetry protect the fermion to be gapless. Okay, now in bosonization, however, okay, in bosonization we introduce order parameters, which is another name for mass term. Thereby, we will break this U1 times U1. We introduce all possible mass term. So all possible mass term means any mass term which anti-commute with the gamma matrix. Okay. We don't care about what symmetry it break and so on. We introduce all mass term. Then we fluctuate the order parameter smoothly to restore the entire charge conjugation, time reversal, and U1 cross U1 symmetry. Okay, so pictorially, this means that I give you the massless fermion theory, I add to it, okay, by hand, smooth in space and time, fluctuating order parameters, bosonic order parameters, to gap the fermion out. Of course, if this order parameter does not obey translation symmetry, is literally I cannot plot this picture, but I think you know what do I mean. Okay. Yeah. Now the fermions with the fluctuating mass term is described by this partition function. So this is the fermion path integral, and this Q control the mass term, which mass term we add. So M, the mass term, is a linear functional of Q, okay? And then we integrate over Q, okay? So this is what do we mean by we introduce the bosonic mass term and fluctuate the mass term smoothly, okay? So the action here is just the free fermion action and plus the mass term. The mass term depend on QC linearly. Okay. Right. Okay. Now, if the this line is a intuitive statement. Okay? If the order parameter fluctuation are very smooth, namely very slowly in space and time, the fermion will remain to be gapped. Okay. So under that condition, fermion can be integrated out to yield a pure bosonic model governing the fluctuation of the order parameter. So, so the nonlinear sigma model action is obtained by integrating out the fermions. Okay? And the path integral now become just the path integral over all configuration of the order parameter. So it turns out that for 1+1d, if the flavor number is greater or equal to 2, such fermion integration produce the level 1 Wess-Zumino-Witten term. Okay? Yeah. So this is an example where I start with a 1+1d complex 1+1d complex 2 flavor fermions. Sorry, previously I was talking about 1 flavor, but in order for the Wess-Zumino-Witten term to exist, the flavor number has to be equal to 2. 2 flavor fermion, we have obtained a effective theory, which is a bosonic theory with nonlinear sigma with the Wess-Zumino-Witten term. Okay, so now let's talk about the anomaly. So the U1 times U1 symmetry is necessarily broken by the lattice regularization. This is because if this Dirac dispersion is the low energy limit of a lattice dispersion. So I'm imagining I have a lattice tight banding model whose low energy dispersion is Dirac. Then the lattice dispersion, however, must obey the periodicity of the Brillouin zone. In one dimension, the Brillouin zone runs from -pi to +pi. So if it is going to obey the periodicity of the Brillouin zone, that means this point has to be identified with this point, and this point has to be identified with that point. However, if you notice that at low energy, this is regarded as the right mover. So this is the right moving branch, and this is the left moving branch. So as the result of lattice regularization, the left and the right moving branch are now connected. Okay. Now, okay, so now let's imagine we insert. So this is a one-dimensional problem. Okay, so this is with lattice point denoted as black circle here. Let's insert a time-dependent flux in the middle of the ring. Okay, and here, this is in a momentum space. Okay, the solid circle means occupied momentum state. The empty circle means unoccupied momentum state. If we insert a time-dependent flux, the derivative of flux with respect to time will induce a EMF. The EMF, let's say, is an electric field which accelerates in one direction. So you see, it moved the K point to the right. So the original K point configuration here now moved to here. And so because the button here is connected, so this field, the circle, will come out here and go in here, and end up having extra field circle above. And this means that the axial current, namely the right current minus the left current, is no longer conserved. In fact, it's pretty easy to show that the d mu j mu 5 is equal to 1/pi times the electric field on the one-dimensional ring. So the chiral U1 symmetry is no longer respected. Okay. However, the total current, which is J mu right plus J mu left, is still conserved. Hence, the diagonal U1 symmetry is respected. So this means that out of the low energy emerging symmetry, TC and the U1 cross U1, TC and the diagonal U1 shows no anomaly. Those are anomaly free. Okay. Now I need to be more thorough. That is, everybody knows that the anomaly in 2+1d in odd space-time dimension is different from the anomaly in even space-time dimension. So now let me talk a little about the anomaly in 2+1d. Again, I take a simple example where the Hamiltonian is given by such a Dirac fermion theory. And the symmetry of it is that it has charge conjugation, it has time reversal, and it has the global U1 symmetry. Now it doesn't have U1 cross U1. It just have a global U1 symmetry. Okay. Now after lattice regularization, okay, if you imagine this is again the low energy limit of some lattice dispersion. Now after lattice regularization, so what does the Hamiltonian look like? It means that the Hamiltonian will be sum over the Brillouin zone of AK times X plus BK times Y. X, Y, Z are again Pauli matrices plus CK times Z. You might wonder, why couldn't I have a identity operator here? It could, but since the identity operator does not affect the gap versus gaplessness at any K point, so it doesn't affect my argument. Okay, so therefore the lattice Hamiltonian is given as such. Very simply, you can show that if the time reversal symmetry here is respected, then you need all those A, B, C to be an odd function of K. Okay, be odd function of K. So, for example, we already see near the center of the Brillouin zone that A is equal to Kx, and C is equal to Ky, and B is equal to 0 as K approach 0. In the neighborhood of 0, 0 to linear order, this is true. But the fact that ABC need to be an odd function of K means that ABC all need to vanish at the 4 time reversal invariant point. What do I mean by time reversal invariant point? I mean, if you negate the momentum here, it will be equal to the original momentum plus a reciprocal lattice vector. That's called a time reversal invariant point. All of those are time reversal invariant. Therefore, ABC all must be equal to 0 here. So that means it's impossible that only at this point the system is gapless. The system, because it is also gapless here, here, and here. So this says that you cannot respect the time reversal symmetry and having gapless spectrum only at K equal to 0, 0. You can ask, then can I regularize and make the spectrum be only gapless at 0, 0? You can do that, but that is at the expense of breaking the time reversal. Ken Wilson taught us how to simply regularize a theory. And here, this is Ken Wilson, this is a lattice model with a Wilson regularization. And for small k and small kx and ky, sin kx approach kx, sin ky approach ky, and the 2 minus cosine kx minus cosine ky is 0 if k approach 0. So this was the low energy limit, the Dirac theory. But here, the adding of the third term is important because if there were no such term, then at kx, ky equal to 0 pi, pi 0, or pi pi, it will also be a gapless. Adding this term is to gap out the fermion at those time reversal invariant point. So if you add this time reversal invariant, so if you add this regularization, this y is a mass term which break time reversal symmetry. You can indeed, in the two-dimensional Brillouin zone, you can indeed see that only the gapless node occur at k equal to 0. It's less obvious, but it's true that if you have such a lattice theory, the effective U1 gauge action is the Chern-Simons form. It has sigma xy equal to 1/2. The reason that those sigma xy come from is coming from the pi 0, 0 pi and the pi pi regularization point. Okay, so yeah, so the bottom line is that although in 2+1 dimension, the continuous UN symmetry has no anomaly, but the discrete time reversal symmetry has an anomaly. Okay, so now let me look at the problem from the topological insulator and the superconductor boundary point of view. Right. The fact that in the previous example, 1D example, if charge conjugation, time reversal, and the U1 cross U1 are respected, we say that there's no allowed mass term. And this certainly suggests that this massless fermion can be realized at the boundary of a topological insulator and superconductor, where the protection symmetry now is C, T, and U1 cross U1. Recall that the so-called symmetry protected topological state is as so long as the protection symmetry are not broken, then the boundary either has to be gapless or something strange has to occur, such as a topological order. Okay. So the fact that this gapless massless fermion theory under those symmetry, they cannot be gap out, suggests that they might be realized at the boundary of a topological insulator or superconductor. Indeed, it turns out that all the massless fermion theories, the complex class, the real class in all dimensions and with different n, we considered in this talk, can be realized at the boundary of a Z classified topological insulator and the superconductor. So topological insulator and superconductor can have different classifications, Z or Z2, and the massless fermion theory we talk about here are the boundary of a Z classified topological insulator and superconductor. Okay, so now the 1+1d massless fermion mode, we have the right mover, we have the left mover. they are the boundary mode, okay, of two different Chern insulators with Chern number plus minus 1. Chern number has to be opposite to each other in order to implement the time reversal symmetry. So the previous non-chiral massless fermion can be viewed as the boundary of two layers of Chern insulators stacked on top of each other. The time reversal, charge conjugation, and U1 times U1 are now exact symmetries because the two Chern insulators each has a conserved charge. This is one U1, and the bottom layer also has a conserved charge, which is another U1. So TC and the U1 cross U1 are exact symmetries in this 2+1 dimensional system. But however, the boundary axial current, namely J mu right minus J mu left, is still not conserved. To see that, all we need to do is again insert the flux tube, time-dependent flux tube, at the center of the Chern insulator, and this will induce an EMF shown by the dashed orange circle. Now this azimuthal EMF will induce current flow, but since the Chern number of the top layer and the bottom layer are opposite, so the current flow in the opposite direction. As the result, the J mu 5, namely the right current minus left current, okay, is not conserved because there's a net J mu 5 flow to the boundary. Again, its anomaly is exactly what we see in the low energy effective theory. So this point of view is pointed out by Callan and Harvey, and it's called the anomaly inflow picture. Okay. Now we are doing the bosonization step. It amounts to we introduce a smoothly fluctuating bosonic order parameter at the boundary of a topological insulator, in this case, two Chern insulator boundary. And after doing so, the boundary theory is a nonlinear sigma model, again, because this boundary order parameter gap out the fermion. And if the boundary order parameter fluctuates smoothly, the fermion remain gapped, and we can integrate them out. So the boundary is left with a nonlinear sigma model. Now, the nonlinear sigma model, which is the bosonic boundary, and the massless free fermion boundary, they must have the same anomaly because they are attached to exactly the same topological bulk, topological insulator. So in particular, you insert flux tube, the current will flow, and the boundary J mu 5 will not be conserved. So it's kind of interesting to ask how is this chiral anomaly? How is the anomaly manifested in the bosonic nonlinear sigma model? It turns out that the anomaly of the nonlinear sigma model is encoded in the Wess-Zumino-Witten term. And this was shown by Wess-Zumino and Witten. Okay. So, right. So again, then at the boundary, if in the 1+1d complex class, if the flavor number is greater or equal to 2, we end up with such nonlinear sigma model with Wess-Zumino-Witten term. since the order parameter fluctuation, so the order parameter fluctuation restore the protection symmetry. Okay, since the protection symmetry is restored by the fluctuation of the order parameter, this nonlinear sigma model should be either gapless or exhibiting topological order. Okay, right. So, but because of the existence of Wess-Zumino-Witten term, the quantum disordered nonlinear sigma model is actually gapless. Therefore, we conjecture that with all symmetry restored, or protection symmetry restored, the quantum disordered nonlinear sigma model and the massless fermion are equivalent. This is the basis of our bosonization.
Can I ask a question here, Dung-Hai?
Yes.
So the question is, what do you mean by the quantum disordered nonlinear sigma model? Isn't even the concept of that regularization dependent? So it could be gapped, it could be gapless.
Right.
Gap with a broken symmetry, or it could be gapless.
Right.
I don't think one can claim there's a universal.
Right. So notice that I emphasize that the quantum. Okay, you're certainly right that the nonlinear sigma model can have spontaneous symmetry breaking and having a gap. Okay, but that I wouldn't call it restore all the symmetries. So I'm saying that with all symmetry restored, the quantum disorder nonlinear sigma model and the massless fermion are equivalent.
Well, so suppose I take like a J1, J2 antiferromagnet on the spin chain.
Mm-hmm.
So that when J2 is bigger than 1/6, it's got a dimerized state. It breaks some internal symmetry.
Right.
I'm not sure whether that's how to say that in terms of the sigma model, but it certainly preserves all the continuous symmetries of the sigma model. And that's a perfectly good regularization of the quantum nonlinear disordered sigma model.
Right. So in the case of spin chain, the dimerization term break a emerging SU2 right times SU2 left symmetry.
Right. Okay.
So here I'm talking about, really you need to respect all the symmetry, even the right and the left, chiral symmetry you have to respect.
I see. Okay, thanks.
But you are restricting to 1+1d, right? Otherwise.
Right. So far, all the example I'm using is 1+1d.
Mm-hmm.
Right.
Maybe a related question. So in your quote-unquote derivation of the nonlinear sigma model, kinematically, there's freedom to choose different OPMs for a given fermionic theory. I think you need to have some knowledge or intuition of the dynamics of the theory in order to decide OPM you choose.
Right. No, for 1+1d and the 3+1d, the OPM is unique. It has only one component. But for 2+1d, you are right. The OPM has several disconnected components, and you need to know which component will break what symmetry in order to, say, which nonlinear sigma model will mimic the massless free fermion with all emerging symmetry. So, for example, if you have n equal to 4, and in 2+1d, the order parameter manifold is U4 over UL times U4 minus L. Only for L equal to 2 manifold, the time reversal symmetry is respected. Therefore, if you want to say, if you want to say it reproduces a massless boson theory with time reversal symmetry, you are restricted to that submanifold.
I actually think even if you choose L not equal to 2, the time reversal symmetry may not be manifest, but is somehow hidden there.
No, the time reversal symmetry will map the L manifold to 4 minus L manifold.
But if you choose L not equal to 2, in that example, you will also have some Chern-Simons term, and there will be
exactly. That's exactly right. So that Chern-Simons term manifests the breaking of time reversal.
I think both the Chern-Simons and the Wess-Zumino-Witten will break. Maybe their summation somehow preserve it. I'm not sure.
No. The Chern-Simons is the result of gauge the Wess-Zumino-Witten. Yeah. In fact, we will talk about that. So in the twist the bilayer graphene application.
Okay.
Maybe I can have just a quick comment because I think the point is that you're talking here about the O4 sigma model for the spin chain, not the O3 sigma model. And it's when you use the O4, I think what you're saying is correct.
Right, exactly. Yeah, in fact, we will go to that topic hopefully pretty soon. Okay, so we conjecture that with all symmetry restored, the quantum disorder nonlinear sigma model and the massless fermion theory are equivalent because they have the same symmetries, they have the same anomalies, they are both gapless, and moreover, the boson theory, the nonlinear sigma model, turn out to have fermionic solitons. Yeah. Right. Okay. So now I'm ready to summarize our bosonization result because I really want to save some time for the applications. Therefore, I will present just the result now. After discussing the applications, if time allows, I will go to more details about the bosonization. Okay, so the bosonization result. So again, the goal is to bosonize two classes of massless fermion theories: complex class with Dirac fermion and real class with Majorana fermion. So the bosonization consists of 4 key parts. Okay, 4 key parts. The first part is the fermion integration. Okay, and to do the fermion integration, we need to know what is the order parameter manifold. How to determine the order parameter manifold? That is, given a massless theory, we have gamma matrix. And then we are asking what is the most general mass term which anti-commute with the gamma matrix, which will open a constant mass gap. Okay, and all such mass term form the order parameter manifold. Okay, so such a calculation is analogous to the calculation in Kitaev's classification of topological insulator and superconductors, except that there the mass term is also under the constraint of symmetry. Here, there's no constraint. You are just given D gamma matrices, and you ask what's the most general mass term which anti-commute with them. Okay, and then you need to show the order parameter manifold will have the D+1 homotopy group will contain a Z factor. Okay, will contain a Z factor, and in order to show the extension, the order parameter extension exists, you need pi d of OPM to be equal to 0. Okay, so here you need to do some for most of the OPM, such as UN and ON, you can just read it from the table, well known in the literature. But for manifold such as UN over 2, UN over 2, or UN over ON, you need to employ the homotopy exact sequence to do the calculation yourself. Okay, if you are interested in, I can show you all the homotopy result. Okay, so this is the first part of fermion integration. The second part is easier, which is to show that the symmetry of the fermion and the boson theory are the same. Okay. The third is to show the anomaly of the fermion and the boson theory are the same. And this required you to be able to deduce the anomaly of the boson theory. And that's required for us to gauge the nonlinear sigma model. Okay. So finally, finally, the fourth part is to show the boson theory has fermionic soliton. That includes the calculation of the homotopy group, D-1's homotopy group. Remember, D is spatial dimension +1. So capital D-1 is pi spatial dimension. So we need to show that the order parameter manifold for the complex class is Z, and the order parameter, the D-1's homotopy group for the real class is Z2. Okay, this is consistent with one being the Dirac fermion and the other is the Majorana fermion. But the actual calculation which determines the Fermi statistics is to compute the Barry's phase associated with a self-rotating soliton. Here, this I don't think you can see clearly, but this is a blob, which means some order parameter configuration, and this configuration is slowly rotating as a function of time. So we need to compute the Barry's phase. Okay. Right, so those are the four parts involved in the bosonization.
Excuse me, Dung-Hai.
Yes.
Question. So here and also earlier when you mentioned this topological phase, you seem to use the free fermion theory classification, just Z2 or Z classes. And here when you discuss homotopy group only, my question is that whether some of the interaction reduction effects is not considered in your discussion or in your theory. I just wonder whether you have some comments about that.
Right. So for the particular example we are consider here, okay, where the massless fermion at the boundary is has a Z classification. So from that point of view, it says that of course that would agree with the free fermion classification. We haven't thought about the subtle interaction effect which will change the free fermion classification. Although I must say the example in which even the generator of the free fermion classification is invalidified is quite rare.
And in this slide, I was wondering, say, whether this similar type of effects also affect the way you look at the homotopy group. In the sense, perhaps you are looking at some defects and whether interaction.
Right. Okay. Good. Okay. Good. Right. So in our discussion here, right. So you are talking about so the homotopy group. Okay. The even lower homotopy group. For example, in 2 dimension, it might say that some point defect is non-trivial. Okay. And then you can think about proliferating the point defect and get some interesting state. The reason that we do not talk about that is because in that case the regularization become very important, because point defect, okay, if you have a lattice theory and you have a point defect. For example, it predict the point defect has 0 mode. Okay, but then knowing that regularization will break the protection symmetry will make it a little bit dangerous to talk about such point defect on a lattice theory. And right, and moreover, if the point defect has a fermion 0 mode, then literally the fermion cannot be integrated out. So here, we really want to consider the situation we can integrate out the fermions.
Can I ask a question?
Yes.
So the fermionic theory, it should require a spin structure to be defined. But then does the bosonic theory, what happens to the spin structure dependence?
What do you mean by the spin structure?
Well, the usual meaning, maybe not familiar with.
It means, for example, if you have a manifold with non-trivial cycle, and when manifold goes through this cycle, let's say S1, you can choose periodic and aperiodic boundary conditions. And those affects the theory that you define on how you choose this periodic and aperiodic conditions. Even if you give the same base manifold, it's an effect of a choice for the -1 comparative.
Yeah,
Okay.
and there are also manifolds that don't have a spin structure, right? So then the theory is only defined on those manifolds.
Okay, so obviously from my answer to the question, this is not a issue we have thought about in detail, and maybe there are interesting stuff lying there, but that's not something which I prepare to speak about.
Oh, can I ask the
I
question?
think this thing comes in through the definition of the Wess-Zumino term. You have exactly the same question in 3+1 dimensions, where there is a nonlinear sigma model of pions with the Wess-Zumino term, whose coefficient is even or odd depending on issues on macroscopically, it's the number of colors and the dependence on spin structure, and that comes in the definition of the Wess-Zumino term, which again makes sense or does not make sense for an odd non-spin manifold or spin manifold. So I assume that the answer to Dominic's question is that this comes in the definition of the Wess-Zumino term.
Thank you.
Okay, but can I ask the question then in a different way? The question is, on the right-hand side, you say that it's a bosonic theory, but maybe it's not the case that this theory can actually be realized from a microscopic lattice model of bosons. Or is that accurate to say? Because a theory with emergent fermions doesn't really exist in a bosonic system unless you have some topological sector or something.
I would think that the fact that we require the order parameter fluctuation to be very smooth, okay, I would think the lattice regularization, when you go to the very long wavelengths and the low energy, it should not has a relevant perturbation. But but our goal here is to bosonize a effective theory, whether just like abelian bosonization, we bosonize linearize the Dirac theory near the Fermi point.
Yeah, the question is whether the bosonic theory is really a bosonic theory or whether it's secretly still a fermionic theory.
So, Dominic, suppose I took a spin 1 chain. Is that a bosonic theory that certainly has a Wess-Zumino term low energy limit?
Yeah, but it doesn't have fermions. Well, I guess in 1D it's hard to really say what fermion or boson is, but in higher dimensions, a bosonic system shouldn't have emergent fermions unless you have topological order or something.
Actually, even in 1D, you can speak of bosons and fermions, local bosons and local fermions. So in nitrogen liquid, we have the bosonized form, but there's still gap with fermions. And that particular nitrogen liquid with the particular operator contents will not be emergent in a bosonic system.
Dominic, your question is already valid in 1+1d. And I think in 1+1d, when people make statement about bosonization or fermionization, in one direction, people sum over the spin structures. In the other direction, people couple to a invertible fermionic topological order. And I assume something similar has to be assumed in higher D as well.
Well, that means that means that you're kind of putting a topological order sector into the theory, right?
Yes.
Right. Okay.
And that's already the case in 1+1d, even though it might not be spelled out in details in every discussion.
I see.
Maybe here, although the nonlinear signal model looks like a theory formulated in terms of bosonic degrees of freedom, but it's really a fermionic theory because we started with the fermionic theory.
Yeah, I mean, yeah, the boson theory certainly has fermionic solitons.
Yeah, this may be important that if a fermionic soliton is not a, it's a local soliton. I mean, it's only changed the local configuration. Then that may suggest the bosonic theory is secretly a fermionic theory because you just modify the local boson field, you can create a fermion soliton, suggesting that in this theory, the fermionic degree freedom is a local excitation.
Yeah.
Yeah, and not like a vortex. I think this fermionic soliton is not like hedgehog, not like a vortex. So
right.
Only local configuration modified.
Right. Exactly. Right.
Maybe a related comment. So maybe a more convenient example is U1 Chern-Simons theory with level 1, where the U1 gauge field is a dynamical gauge field. It also looks like a theory formulated in terms of bosonic degree of freedom, but it's a fermionic theory.
Sorry, what? So far, I haven't talked about the gauge field yet.
Sorry to interrupt. Maybe we can continue this discussion later. I think Dung-Hai, you have only 10 minutes left.
Oh my God!
I think you should speed up.
Okay. I think we don't need to cut the speakers.
Yeah, we don't need to cut, but I think maybe we move this discussion later.
Yes, I agree. So Dung-Hai, please.
Okay. All right. So here is the summary of the bosonization result for the complex class 1+1, 2+1, and 3+1, and for the flavor number greater or equal to 2, 4, and 3, then the appropriate homotopy group tells you that the Wess-Zumino-Witten term could exist. And then we do the fermion integration to explicitly show that it does exist. And then for the real class, those are the bosonized model. And here, all the parameter is depend on dimensions is different. And here for 1D, n has to be greater or equal to 3, n has to be greater or equal to 6 in 2+1, and n has to be greater or equal to 3 in 3+1. And fortunately, in all the examples we shall talk about, this bound in n is satisfied. So that's
something here which I'm confused about. I think I understand the first line as a statement that this defines this is a well-defined bosonic field theory in 1+1 dimensions, which is dual to a theory of fermions. That's the part I understand. The way I read the second and third statement is that these are non-renormalizable field theories in 2+1 and 3+1 dimensions correspond. The first is 2+1 and the second is 3+1. These are non-renormalizable field theories, and you need to specify more information to describe what they do. And at low energies, these are bosonic theories of boson, not of fermions. At best, you could say that there's a deformation of this system with the same symmetries and the same anomalies, where after a phase transition, the bosons are gone and we see massless fermions.
Right.
But this is fundamentally different than in the first case.
Right. You are quite right. So in fact, for the 2-dimension case, there is a stiffness parameter where lambda 3 has a dimension of length. And for 3-dimension, you have a stiffness term with lambda 4 square, where lambda 4 again has a dimension of length. And depend on this coupling strength, you can be in the spontaneous symmetry breaking phase, you can in the quantum disorder phase.
No, I'm sorry, that's exactly what I object to. The dimension, this parameter is dimension 4. And what these equations mean is this is an effective theory at low energies smaller than the scale set by lambda 3 or lambda 4. And this theory is not well defined at higher energies.
Right.
So you can't just say, look at this Lagrangian and consider the limit that lambda 3 or lambda 4 go to infinity.
Yeah, I mean, I don't, you know, I'm considering a explicit finite cutoff imposed on this theory.
But then the answers will depend on the cutoff. You cannot just take this thing as is and lambda 3 and go to strong coupling in lambda 3 and lambda 4.
Right. So you know, I imagine given a finite cutoff, I will have some value of lambda 3 and lambda 4, and depend on the value of lambda 3 and lambda 4, my sigma model can be in different phases.
But what the theory does depends on a lot more information that you did not spell out. It depends on what happens at the cutoff, exactly how you regularize it, and so forth.
Yeah.
You cannot make universal statements based on these two Lagrangians.
Right, but I think how do you regularize will be content in this dimension 4 parameters.
Well, I can use Pauli-Villar's regularization. I can put it on the lattice. I can put it on the lattice and add more interactions at short distances. I can do it all sorts of different ways, and the physical answers will depend on that.
Yeah, so all I'm saying is that there exists a range of lambda here viewed as the stiffness parameter in which the theory will be quantum disorder and massless.
I don't know what it means. Lambda 3 is a set of scale. This is the only dimensionful parameter in the theory. So you can say that the scale of lambda 3 is, I don't know, 50 MEVs, 50 EVs, whatever scale you want. And that's it. It doesn't mean anything to say lambda 3 is large.
Right, but in condensed matter physics, we fix a value of the cutoff and look at the low energy behavior of this sigma model. We don't ask what happened when the cutoff diverges.
Right, but that means that you did not specify the theory. You specified the theory at energies far below the cutoff.
Yeah.
With lambda 3, so imagine the scale of lambda 3 is given by the cutoff. Yeah. And this effective Lagrangian is valid only at energies far below the cutoff.
Right.
If you go to higher energies, you need to include high derivative corrections.
Yeah, absolutely.
And these high derivative corrections exist even in condensed matter physics.
Yeah, I mean, absolutely. But I'm not going to go to, you know, I'm not going to claim that this theory applied to arbitrarily short distance.
But you are going to claim that this theory, as appeared on this slide, is the same as a free massless fermion.
Right. I'm only claim that this theory with lambda chosen in certain range, okay, at low energy, okay, is equivalent to the massless free fermion theory.
Okay.
Yeah, maybe I can put this question in a different point of view. That is, suppose we fix cutoff to be 1. Then if lambda is very, very small, this theory may have a spontaneous symmetry breaking. So it's an ordered fix. Then you can imagine we increase lambda approaching some kind of critical point where symmetry get restored.
Right.
I think your proposal is that some critical point actually is this massless Dirac fermion.
Right. Beyond the critical point.
Okay. If you go over the critical point.
Right. Right.
I see. Yeah, I'm thinking at critical point. Yeah. But anyway, yeah. Thank you.
I think what you're really saying is that is that you have a microscopic system, and at low energies, that system has 2 phases. In one of them, the low energy action is, sorry, as appearing on this slide. And in the other phase, you have massless fermions. That's a statement I understand. But I don't think that the massless fermion theory is in any sense a strong coupling limit of the action on this slide. I have no problem with the statement with 2 phases. If you say that there exists a system you did not describe, which has 2 phases, one of them described by the action on this slide, and the other corresponds to a massless fermion.
Okay,
I have no problem with that statement.
So would it be helpful if I show you something which I prepared?
Okay.
On this.
Okay, sorry that I interrupted.
Okay, so. Oops. Okay. Right. So I claim that that nonlinear sigma model we are considering is the low energy effective theory of an interacting fermion model. Okay, and the interacting fermion model consists of the usual Dirac fermion free, the massless free fermion part, and the interaction is precisely this fermion bilinear coupled to the mass matrix. Okay, and now this Q does not yet have the constraint that trace Q dagger Q is equal to 1. So I consider, so this Q is considered as a auxiliary field. If you integrate out the auxiliary field, this is an interacting fermion problem. Okay. Now suppose you have a phase where the trace Q dagger Q is greater than 0, okay, but yet the Q itself can so this is similar to symmetry breaking, and the Q itself is fluctuating as the Gaussian mode. Then the low energy theory is the sigma model I presented. And as a function of this fermion, 4 fermion coupling strengths, there's a mean field transition where Q dagger Q begin to be non-zero, but there's an interval in where although trace Q dagger and then go to a symmetry breaking phase where the average Q becomes non-zero. It's in this phase. It is in this phase that I was talking about.
It seems we can ask a lot of these questions in a context more familiar to condensed matter physicists. That is, like if you have a gapless Fermi liquid, what good it would do if you use the BCS order parameter, like this partial theta, where the theta is the angle of the condensation, to rewrite the gapless Fermi liquid.
Yeah, right. You are not guaranteed that you can write gapless Fermi liquid with any bosonic, order parameter. So this scenario is more like the local moment formation in condensed matter physics. At this mean field level, the local moment form, but the direction of the local moment still is fluctuating. It still can give you a quantum disordered phase, okay? And then if even the direction fluctuation of the local moment has become spontaneous symmetry breaking, then you have, ferromagnetism or anti-ferromagnetism and so on. So this is entirely in analogy with those. Okay, so I guess should I at least spend some time on the application?
Yes, please.
Yes, please. We don't have a time constraint. Yeah.
Okay, so I guess I will only have time to talk about one application.
Actually, I think you could just go on with your plan, and then maybe if you want, you can summarize some of the results first, and if people want to leave, they can leave, and you can continue to finish everything you want to say and prepare anything you have prepared, basically. So okay. So really don't feel, even if you want to spend another 1 hour, 2 hours, it's really not a problem. It's really not a problem.
Okay.
There are people speak for 3 hours or more.
Okay, yeah. Okay, so now let me talk about the first application. The application is the SU2 gauge theory of pi flux phase. I think this subject should be familiar with many condensed matter people, but let me still pedagogically say a few words. So the SU2 gauge theory of the pi flux phase. The system we consider is Hubbard model. So Hubbard model, as you know, below the Mott-Hubbard gap, the double occupation of site is prohibited, and the effective Hamiltonian is a spin Hamiltonian, and the Hilbert space is that of the tensor product of the spin Hilbert space. Okay. Now, right. Now, in the so-called spin-on theory, we put back the fermion and write the spin operator as a spin-on bilinear. But now we impose the constraint that the following three constraints, that the Hilbert space is annihilated by annihilating two fermion on the same side, creating two fermion on the same side, or acting on the number operator -1. So they will all give you 0 if the occupation per site is 1. So this is so-called the SU2 constraint. Now, then to proceed, this is what condensed matter physicists do. Because the fermion, the spin-spin interaction, the spin itself is already quadratic in fermion. So the spin-spin interaction is a 4 fermion interaction. And we don't quite feel comfortable of handling 4 fermion interactions. So Hubbard-Stratonovich decouple the 4 fermion interaction into spin-on bilinear coupled to auxiliary field. Okay. And then we implement the 3 constraints here by Lagrange multiplier, and those Lagrange multiplier become the time component of the SU2 gauge field. So symbolically, the partition function is equal to the spin-on path integral followed by the auxiliary field integral and integrating over the Lagrange multiplier. Okay, and the action consists of fermion, auxiliary field, and the gauge field. And this has been discussed in detail by Patrick Xiaogang and Naoto's review of modern physics work. Okay, then the next thing we do is we find a saddle point of that partition function. Find the saddle point. And the famous famous saddle point is the pi flux phase of Affleck and Marsden, where the auxiliary field take the form of a tight binding model, okay? And the Lagrange multiplier in the saddle point are all equal to 0. And this is called the pi flux phase. By the way, here, the gray bond and the green bond means that has a sign difference. It's called a pi flux phase if you hop around any plaquette using this tight binding model. You'll find the result is -1. So every plaquette has enclosed a pi flux phase. So this tight binding model in momentum space has 2 Dirac points, one at momentum 0, 0, and the other at momentum 0 pi. Okay. Now, so then the next is to identify the low energy fluctuation of the auxiliary field. This is the mean field. Identify the low energy fluctuation of the auxiliary field as the spatial component of the SU2 gauge field. So at the end, we end up with a low energy field theory where we have a fermion coupled to SU2 gauge field. And here, I should say that this fermion is a Majorana fermion field. The reason we use the Majorana rather than the complex fermion field is because the constraint does not conserve the spin-on number, okay? So we have a Majorana field and coupled to a SU2 gauge field, and this TB is the SU2 a generator. This is called the charge SU2, not to be confused with the spin SU2. So we end up with masses fermions of the pi flux phase coupled to a SU2 gauge field. Okay. Right. Then what's the flavor number? The flavor degree of freedom consists of Majorana, tensor spin, and tensor valley, right? Because of the there are 2 Dirac points, so there are 2 valley. So totally the flavor number is n equal to 8, and this is a real class. This is n equal to 8 in real class. Okay, so here is the bosonized pi flux phase. This is the Wess-Zumino-Witten theory. Okay, this is the nonlinear sigma model, but this is just the pi flux phase, free fermion. So if we want to couple it to the SU2 gauge field, we need to know how to gauge, in particular SU2, charge SU2 gauge this nonlinear sigma model. And we learned how to gauge this model from Witten's work in nuclear physics B. That is a bit long, so I wouldn't want to explain it in detail, but this is the result, okay? So the gauge, the nonlinear sigma model, so here we consider the most general 08 gauge field, okay? So we gauge the nonlinear sigma model, right? And now, but the problem at hand is that the gauge field is not 08, is a subgroup of 08, is the charge SU2. So we can then consider restricting the gauge group from 08 to charge SU2. And moreover, now let's consider the effect of the SU2 gauge field is to mediate confinement. Okay, I'm not saying the deconfined phase doesn't exist. I'm only saying that let's consider the confined phase. So to deal with the SU2 charge SU2 confinement, we again use Witten's effective theory idea of QCD. And the essential idea is that to identify the mass term associated with this boson field QR, as this is a particle hole mass term, which is the analog of a meson. Okay. Now, charge SU2 confinement means the meson all have to be a charge SU2 singlet, which means that charge SU2 singlet means that if you take the mass term associated with QR, it must commute with the charge SU2 generators. Okay. Now, so it's pretty easy because charge SU2 generator can be written down simply, and so it's Y times QR. So the end result is that we find the following solution. One solution can be found in the L equal to 4 manifold, namely OA, quotient O4 times O4, order parameter manifold. In this manifold, there exists a QR which commute with the charge SU2 generator. And this QR can be written as a linear combination of 5 masses. And it can be shown that 3 of the mass turn on antiferromagnetic order, and the other 2 mass turn on a VBS order. Okay, and the coefficient, because QR need to satisfy QR squared equal to 1, so the sum over the coefficient squared is equal to 1. And moreover, after such QR confinement, that QR is commuting with the SU2 generator, this resulting QR restricted in this form no longer coupled to the SU2 gauge field. So now we just plug this QR, okay, into the previous bosonized theory, and the result is the O5 nonlinear sigma model, which Tanaka and Hu first point out. Okay, it's the O5 nonlinear sigma model, and this nonlinear sigma model describe the phase transition between antiferromagnetic state and the VBS state. Earlier work of Holden and Reed and Sachdev has argued that with no frustration, when you destroy the antiferromagnetic order, you will enter into a VBS, valence bound state. And this critical point was first discussed by Santo et al. And by Tanaka and Hu, and also by Su and Sachdev, which they not consider a SU2 gauge theory, but they consider a U1 gauge field theory of a staggered flux phase. Anyway, grossly, their conclusion is in agreement with that you have a O5 nonlinear sigma model describing the phase transition. Okay, so it's first very satisfying that by the SU2 confinement you will capture the permanent order in a non-frustrated lattice, and they also will capture the phase transition. I should say that, however, once you confine the order parameter to the O5 manifold, it no longer has solitons. Okay, right. That's one solution. Another solution can be found in a different mass manifold, O8 quotient O8 times O0, or O8 quotient O0 times O8, where Q becomes just a constant, And if you put a spin SU2 gauge field to probe this state, you get the effective spin SU2 gauge action is the SU2 level 1 Chern-Simons theory. And I read from Xiaogang's book that this is the effective gauge action of chiral spin liquid. Right. So that's the application to the SU2 gauge to the pi flux phase SU2 gauge theory. By just straightforward extending the argument above, we can consider the following. We consider 3 tight binding model, okay, where the tight binding model each is charged SU2 invariant, okay. This is the analogy of the pi flux phase tight binding model. Okay. In this tight binding model, the arrows, okay, point in the direction where the hopping is IT. So it's always imaginary hopping IT. But this hopping model is related to a nearest neighbor real hopping model by a site-dependent gauge transformation. Okay. I should say that in 3D, the interlayer hopping from between the A sublattice and B sublattice, this is a 4 sublattice model. The real hopping has opposite sign. So this is the analog of the pi flux phase mean field theory, but we construct it as a real tight binding model. Now, upon the SU2 confinement, in 1+1d, we simply get the whole 4 nonlinear sigma model with the Wess-Zumino-Witten term. Here we know that this is the effective action of the anti-ferromagnetic Heisenberg model. In 2+1d, it becomes this 05 nonlinear sigma model we speak about. Okay. In 3+1d, there's extra complication, namely this is a U1 cross 06 nonlinear sigma model, where the U1 piece actually decoupled from the 06 piece. Okay. We can gap out the U1 piece. So this model are the generalization of the critical spin liquid. If we call the 1+1 dimensional theory the critical spin liquid, this is the generalization of the critical spin liquid. They are the effective theory after the Dirac semi-metal turn Mott insulating. Okay, so that's a short discussion. Okay, and the second application. Okay, in the third application, we talk about the twisted bilayer graphene. By the way, I'm very new to this area, so so if I say something, you know, stupid, please tell me. So in the momentum space and in the real space, the bilayer graphene look like that. And the band structure of the twisted bilayer graphene consists of 8 narrow bands in the midst of all the other bands. So we focus on this 8 narrow band. Right. In the following, I shall focus on integer filling factors. So filling factor means that in each Moiré unit cell, how many electrons, and at the charge neutrality point, it is 4. So we measure the integer filling factor relative to the charge neutrality. So if you see nu equal to 0, that means it is the charge neutral point. The reason that I focus on integer filling factors is because I saw an interesting paper which claimed that at integer filling, they are Dirac revivals. Okay? and since if they are Dirac revivals, then we can use our massless relativistic massless fermion theories. Okay. Now, second, because there's no sign of superconductivity at integer filling factors, so the class is a complex class. Okay, so we are talking about complex class at various integer fillings. Okay, so at nu equal to 0, the Fermi level pass through the Dirac point. In the following, oh, I lost my, okay, I lost my laser point. Okay, in the following, we should focus on the band structure where the Dirac point exists, and the bandwidth is narrow but not flat. So I find it very difficult to think about the flat band. The assumption is that if the correlation energy is greater than the bandwidth, the physics at magic twisting angle should recover. Okay. So so here the flavor degree of freedom consists of the graphene value tensor the spin times the Maury value. So this is n equal to 8. Okay, so the bosonized theory is n equal to 8 nonlinear sigma model because it's in the complex class. So this there are 9 different mass disconnected mass manifold, and each mass manifold is characterized by trace of Q. So Q has, because Q squared is equal to 1, so Q has a plus minus 1 eigenvalues. So L just label how many eigenvalue are plus and how many eigenvalue are minus. So there are this 9 mass manifold. Now let me gauge that nonlinear sigma model with only the electromagnetic U1 gauge field. So this is the usual Maxwell gauge field. The gauge, the nonlinear sigma model, read like this, and you notice the second term is just the Chern-Simons term, and the coefficient of Chern-Simons term is determined by trace of Q. So that means the sigma xy is equal to L minus 4. So among those 9 different mass manifold, only the middle one has sigma xy equal to 0, and hence conserve time reversal symmetry. So experimentally, the measurement tell us that the sigma xy is 0 at the nu equal to 0, and this places us at this middle mass manifold. And there are 2 roots. One is that if QC has no spontaneous symmetry breaking, then the fermion remain massless. So this is a semi-metal phase. And the other is for QC to spontaneous break symmetry, and that become a symmetry breaking insulator. All right, how about other filling factors?
Excuse me, Dung-Hai, may I ask a question?
Yeah. Yes.
Yes. Oh, sorry, I think I should even ask earlier. Maybe there are also people want to ask questions, so I think it's still okay to ask. I want to make sure I understand the first application compared with the third one. The first one is this pi flux mean field. Originally, it's a fermionic theory, right?
Yes.
You also get this effective real fermion numbers, n is 8, including Marana, spin, and possibly other, I forget, maybe Valley. There's 8.
Right.
And the graphene is also 8, correct?
Right. But the graphene is a complex class.
Oh, okay. Complex. Is complex fermion in that case?
Yeah.
Okay.
Yeah.
All right. Okay. Then detailed question is that I just want to be updated about the contribution of your work. Is that you start from a fermionic theory and use the bosonization method that vary when n is larger or equal to 6 for the real fermion, right?
Right.
And apply that to find out the bosonized theory.
Right.
And we have some discussion earlier. Subtlety was that when you try to do bosonization, actually you sum over spin structure. But that's fine. Probably you get some effective field theory for the bosonic theory. And now you look at the possible phases that this bosonic nonlinear sigma model can go to.
Right. Are you talking about the pi flux phase at this point?
Yes, the pi flux. You
Okay,
photo that one. And
then I impose the SU2 confinement.
Okay.
So if I don't impose SU2 confinement, I get a O8 over OL times OA minus L sigma model. So if I impose a gauge field, okay, if I gauge this sigma model, I get the following result. But since the pi flux phase coupled to only the charge SU2 gauge field, so I restrict myself to a charge SU2 subgroup of O8, and then I consider the charge SU2 confinement. That means I need to require that the mass term to be commute with the charge SU2 generator. And this additional constraint forced me to be in the sub-manifold. So that constraint has two solutions. One solution is in this sub-manifold, okay? And but instead of QR can vary in the entire such sub-manifold, is constrained to be equal to S4 to lie in a sub-manifold of this, which, and if I put in the QR in this form, it will give rise to the O5 nonlinear sigma model.
Okay, so may I interpret this way? So you bosonize the pi flux fermionic infield theory and get some possibly maybe a model theory in some way, but it's bosonized. So that's not quite, up to the discussion we had about the bosonization subtlety about summing over spin structure, etc. Then you get a model theory, and then you do a SU2 confinement, you say?
Yeah.
And then you land it with another theory, then you can explore the consequence IR phases, in which you have AFM and VBS.
Right.
And these phases is not obviously, I just want to make sure is that this AF and the VBS cannot be easily accessed directly from the pi flux mean field from your theory?
No. This VBS and the anti-ferromagnetic and VBS is among a whole zoo of possible mass term of the pi flux phase.
Okay. So what will be I just want to make sure, then what will be the surprising fact we should take?
No, so the surprising fact is that the SU2 charge confinement pick up those 5 as the only possible mass term.
Okay. So you give some constraint on the bosonized theory, then you can land up with the physical sensible phases. And
right. That's right. So the constraint is precisely the mass term has to commute with the charge SU2 generator.
Okay. What are the surprising, maybe like new insight about doing all this procedure? Maybe I didn't get something is interesting, but I want to know what's the new insight along doing this.
Well, first of all, treating the gauge field fluctuation in particular, consider is in the confined phase, has not been done, right? It's not as simple as it can be said, but it turns out that in this non-abelian bosonization, using this Witten's method for effective QCD, this just amounts to requiring the mass term to commute with the charge SU2 generator. So you can actually you can actually treat the SU2 confinement.
Okay.
Actually, I think there are previous papers in doing this.
Yeah. So this theory was first proposed by Tanaka and Hu, and they basically ignore the SU2 charge confinement, and they simply say that, okay, the order parameter can either be antiferromagnetism or VBS, and then they integrate out the fermions. That's the way they approach this problem. But the original problem has the SU2 gauge fluctuation, which is ignored.
Yeah, I mean, including the SU2 gauge fluctuations. I think there are papers doing that.
Oh, okay, okay. So please then give me the reference.
Mm-hmm. Sure.
Yeah, I just use this as the example of how is this bosonization can be applied. Okay. Okay, are there?
And also you have the solution to the chiral spin liquid.
Right.
Are these also known before, or you give a different perspective on that? Just
no, chiral spin liquid.
The way you derive, maybe it's new, or what's the emphasis on?
Chiral spin liquid certainly is known. I mean, I'm not discovering the chiral spin liquid. Perhaps it is amusing that this just turned out to be one of the solutions of the SU2 charge confinement.
Well, then I can just interpret your result as bosonize some model theory that can end up with many IR phases people propose.
Yeah.
Okay, that's right.
Yeah.
Thank you.
Yeah. Yeah. Right. So should I stop or keep going?
Keep going. And if you need to take a break, you can take a drink.
I might as well just get it over with. Where were I?
You are in the third example, I think, show this.
Okay. So right. So I was saying that because experimentally at nu equal to 0, there's no sigma xy. Sigma xy is 0. So that places us at the L equal to 4 mass manifold, and then there are then the system has two possible fate. One is if QC acquire a excitation value, it spontaneously break symmetry and becomes a symmetry breaking insulator, and the other is that QC do not break any symmetry and maintain massless, and this is the semi-metal phase. Okay, so now I want to talk about other integer filling factors. Okay, so experimentally, okay, it is observed that at other integer filling factor like nu equal to 1, 2, 3, and so on, there's a compressibility jump at integer filling factors. And I particularly enjoy reading this paper because we can use it. That paper, the author interpreted this phenomena as a Dirac revival, okay, where they say the chemical potential is reset to the Dirac point at moderate temperatures. Moreover, they attribute the Dirac revival to the flavor polarization, analogous to the spin polarization in narrowband metals. Okay, right. So because we can use this, that caught my attention. So in the following, we shall assume, okay, we shall assume the validity of the Dirac revival theory and regard the revived massless fermion theory as a good starting point for understanding lower temperature phases. Okay, that's our position. Okay, now about the flavor polarization, we will take the simplest flavor polarization mechanism, where this is the massless Dirac theory at nu equal to 0. Okay, and the Pauli matrices here are the sublattice, graphene valley, spin, and the Maury valley. Okay, those are what the Pauli matrix act upon. And now, how do we impose flavor polarization? Oops. Well, that's by adding a term to this simple Hamiltonian, which I add delta is a number. Okay, is the amount that will shift the band, and V is a matrix. Okay, it satisfies the constraint that V commute with all the lambda. So V, unlike mass matrices anti-commute with the gammas, but V commute with them, and V squared is equal to 1 because the gap, the amount of shift is already specified in delta P. I also want this V to act as an identity in the Maury valley space, because otherwise it will give the two Maury valley different shift, and that will not give rise to the Dirac point. Okay, so let me see. Are there anything else? Okay, so it can be shown that after a simple basis transformation, this V can be written as identity matrix. In the middle, there's a 4x4 Hermitian matrix, and followed by a identity matrix. And the different flavor polarization pattern is encoded in the trace of P. Okay. So first, let me talk about nu equal to 1. For nu equal to 1, according to Zondinger et al., the polarization is such that 6 bands move up and 1 band move down. So this distance is delta P in the previous slide. So each band is a 3-4 degenerate here, and the flavor number reduced for the Fermi level intersecting bands, N is reduced from 8 to 6. So we end up with N equal to 6 complex class. Okay. So this requires that polarization matrix P in the last slide to have a trace equal to 2. So this polarization matrix lie in a manifold which is U4 over U3 times U3. And this, please do not confuse this manifold with the mass manifold. This is a different polarization manifold. Okay. So after the polarization, the relevant band, namely the Fermi level crossing band, is described by a massless fermion theory, except that its gamma matrices are now projected into the polarization equal to +1 subspace. Okay, so then the bosonized nonlinear sigma model then is N equal to 6 nonlinear sigma model. Again, here I couple it to the electromagnetic U1 gauge field, Maxwell gauge field. And the second term here imply that the sigma xy is related to the trace. And for the 6 different for the 7 different mass components, the middle 3 has sigma xy equal to 0, and the others has non-zero sigma xy. So yeah, so in particular, I want to emphasize that this result is insensitive to the precise polarization matrix. Remember, P belongs to a manifold, U4 over U1 times U3. So it has a lot of choices, but for any choice of P, this will be the sigma xy. Okay, again, experimentally, the measure sigma xy is 0 at B equal to 0. Therefore, again, there are 2 fates. We put L at this a particular L equal to 3 mass manifold, and if there's no more symmetry breaking, namely if QC expectation value is 0, it's a semi-metal. If QC expectation value is non-zero, it can gap out the system. Now, nu equal to 2.
Dung-Hai, I have a question, if I may, about this.
Yes.
Imagine that I see that nu equal to 1. If I understand correctly, the low energy degrees of freedom are Dirac particles in this picture.
Yeah.
Now, let's say that I add 1 electron on top of this, or take 1 away.
Yeah.
It seems to me that this would be symmetric. In other words, it would be symmetric around a non-zero integer. And so, in fact, the compressibility will not show a jump. The compressibility will just have a V shape, or whatever. It would be symmetric about this point. But in fact, the compressibility is highly asymmetric. If you approach nu equal to 1 from above and from below, it's quite different.
Right. So this naive Dirac band I use at absolute lower energy is of course particle hole symmetric. But as pointed out in Zoninger et al.'s paper, if you look at the real band structure, as you deviate from the Dirac point, then it is not particle hole symmetric. They use that as the explanation of the compressibility jump being not symmetric.
Yeah, I mean, experimentally, there is no indication of any regime near non-zero integer of particle hole symmetry around the non-zero integer. In fact, as you know, there's a different theory for this, which I think accounts for this, that does not use Dirac revivals.
Right. I said that at the beginning that we adopt the theory of the Dirac revival. Whether that theory itself will hold water, that's not something I'm ready to answer. But I guess coming to the point we discussed about the degeneracy of Landau fan, it was pointed out to me that there's a paper recently by Santos group, which studied the effect of C3 symmetry breaking. Precisely, it seems to can explain the experimental, Landau fan structure. So therefore, it seemed to indicate that if I start with the Dirac revival theory, but just at low temperatures, I allow either explicit or spontaneous C3 symmetry breaking, then it can understand the Landau fan. Yeah, I understand.
That's consistent with our picture, actually. Yeah.
So this doesn't mean that at high temperatures, okay, I cannot take a Dirac revival as the starting point.
How high of a temperature are we talking about here?
I don't know, like 100 Kelvin. I don't know. So there's a recent paper by Andreas Young's group, which shows that at the high temperature, you have a compressibility jump already.
Right, but that's already asymmetric. It's not symmetric around non-zero integers.
Right, where the polarization matrix has not acquired long range order yet. And here I'm just pointing that just like any order parameter, the polarization order parameter can fluctuate in a mass manifold. Yeah. Okay. So I'm not ready to defend. You know, I would say that at ultra low energy, you are right. If it is a Dirac revival, it should be particle hole symmetric. But however, I was told that you know, one thing is that the band is quite narrow. So as I raise the energy a little bit, the particle hole symmetry is not there. Yeah. So yeah, I'm not ready to defend the Dirac revival theory. I'm just saying, okay, if I assume that theory is hold, this is our analysis.
Thank you.
Okay, so where were I? Yeah, so this result is insensitive to the precise polarization matrix P. Okay, yeah, so experimentally the sigma xy at b equal to 0 is 0, so that places us at L equal to 3, and no symmetry breaking Dirac semi-metal, or it can become a spontaneous symmetry breaking insulator. For nu equal to 2, according to Zondinger et al., so there are 4 bands which shift up and 4 bands shift down. So each band is 2,4 degenerate, and that reduces the flavor number from 8 to 4. Okay, and this would require that the trace of the P matrix in earlier slide to be 0, because 2 of the eigenvalues plus, 2 of the eigenvalues minus. So P is now in U4 over U2 cross U2, and the Fermi level crossing relevant band is described by this massless fermion theory. Again, the gamma now is the original gamma project into the V equal to +1 subspace. So now the gauge, the nonlinear sigma model is the n equal to 4. So again, the same story, with the electromagnetic U1 gauge field coupled to the sigma model. This is the result. By the way, this term measures the soliton charge. This term measures the soliton charge. And due to the second term, you have a sigma xy equal to L equal to 2. Equal to L minus 2. So again, experimentally, sigma xy is equal to 0 at b equal to 0. That places us in for this particular mass manifold. So then the story continue. So it can either be in a semi-metal phase or it can be in a symmetry breaking insulator phase. So finally, let's go to nu equal to 3. So according to Zondinger et al., at nu equal to 3, 6 bands shift down and 1 band shift up, and the Fermi level passing through the band which shift up. So each band here is 1,4 degenerate, and n is reduced from 8 to 2. So this places us as n equal to 2 complex class. And this requires us to have the trace of the P matrix equal to -2. So in this case, P is in the manifold U4 over U1 times U3. And the Fermi level crossing band is described by Kepler's massless fermion theory, where this gamma are, again, the original gamma project into the V equal to +1 subspace. But this time, so again, this is the gauge, the U1 gauge, the nonlinear sigma model. It predicts that sigma xy is L minus 1. But this time, there's experimental evidence that at 0 field, for filling factor equal to 3, when the twisted bilayer graphene is aligned with hexagonal boron nitride substrate, it shows a zero field Hall conductance, and this will require us. I guess I regard this as a spontaneous symmetry breaking. So if sigma xy is just equal to 1, it will place us at this mass manifold. If sigma xy can be also -1, then this mass manifold is also allowed. Okay. Yeah, but now it comes to the question of how about the central mass manifold. This mass manifold is U2 over U1 cross U1, or in other words, is S2. For this mass manifold, the homotopy group is that the D+1's homotopy group is Z2, and the D's homotopy group is Z. And in fact, this model has been studied, and this model is the Hopf sigma model. And the Hopf term reflect that pi3 is Z. And this model still has fermionic solitons. Okay. All right. So, in summary, we have carried out a non-abelian bosonization for the massless relativistic fermion theories in 2 and 3 dimensions, and we apply the bosonization result to the SU2 gauge theory for the pi flux phase of half-field Hubbard model and critical spin liquid in 1, 2, 3 dimensions and the twisted bilayer graphene. With that, I thank you for your patience, and so many of you are still staying. Thank you for the opportunity to speak.
Thank you very much. Thank you, Dung-Hai, for the wonderful, patient lecture. A question or comments from the audience, please.
I still want to ask about the freedom in choosing the order parameter manifold.
Yeah.
So suppose I start with, say, 4 Dirac fermions without coupling to any gauge field.
4 Dirac fermions? What do you mean?
I start with 4 Dirac cones. Say in 2+1d.
Okay.
And they are not coupled to any gauge field.
So spin 4, complex or real?
Complex.
Complex. So you have a complex class with 4 Dirac cone and each with a spin, right?
I mean, maybe in the specific realization, maybe let's say we have 2 spins and 2 valleys. So we in total have 4 Dirac fermions.
I'm sorry. So if with a spin, I would say the flavor number is 8, right?
Okay, then your language is 8.
No, so yeah.
Yeah, no, I just want to say in total we have, say, 4 or 8 flavors of Dirac fermions.
You have what? Sorry?
4 or 8 flavors of Dirac fermions.
4 or 8?
Yeah, either 4 or 8. I just want to give an example. Either 4 or 8 is fine. Let's say 4 in total, including spin and valley.
No, but if you have 4 valley and you have 2 spin, that's 8.
Okay, then let's say 8. I meant including both valley and spin is either 4 or 8. Let's say 8.
Okay.
Then it has a large symmetry, the continuous part. If I stick to the complex case, the continuous part already has a U8 symmetry.
Right.
And now when I choose the order parameter manifold, I can have freedom. So the order parameter manifold is determined by the original symmetry and the remaining symmetry after symmetry breaking. Suppose the original symmetry, let's say U8, and the remaining symmetry is some G. So the order parameter manifold is
so
U8.
for us, the order parameter manifold it's just all the mass term anti-commuting with the gamma matrix and the square root of 1. It doesn't know of the symmetry yet.
I know, but I think your choice is just a particular choice.
Wait, why? Because I include all the possible mass term anti-commuting with the gamma matrix. The symmetry will reflect on how does the bosonic order parameter transform. Okay. Yeah. So I don't use the symmetry to constrain the mass manifold yet.
Let me do it. Suppose I do it. So by choosing different remaining symmetries, I have different order parameter manifolds that may be different from your choice. Can I do this?
No. I mean, if the symmetry, if you have the real, if you have the complex class, and if you have the flavor number equal to 8, okay, then our mass manifold is fixed.
Why?
Because if you just ask, how many, what are the all possible mass terms which can gap out the fermions, and those mass terms form some, 9 continuous component, UA over UL times UA minus L. So our mass manifold doesn't depend on the symmetry. The symmetry come in later as how does it act on the mass order parameter.
I think we are saying the same thing using different languages. So yes, maybe let me switch to a language. So in your case, the manifold is, I think you wrote it as a product of a bunch of Grassmann manifolds, U8 mod UL times U8 minus L.
Right.
And but I can choose only one of the components to be my order parameter.
Right. Certainly, you can change. You can choose one of the component, but notice that by picking a particular component, you might have, broken some, symmetry.
Yeah. This is the question I want to ask. Suppose I choose 2 different L's, say L1 and L2.
Right.
And then maybe for L1, I have this symmetry. For L2, I have the other symmetry.
Right. So as far as I know that if you pick different L, unless L equal to 4, the time reversal is broken. But if you fluctuate the order parameter uniformly around all those other mass manifold, the UA symmetry can be restored. The charge conjugation symmetry is respected.
Let me choose L equal to 3, for example.
Okay.
And this can, as you said, it can gap out the fermions.
Yeah.
And I can already at least formally integrate out the fermions to obtain whatever theory I have. Suppose I'm able to do this exactly without any approximation.
Right, sorry. So when I reach the level of mass manifold for the boson order parameter, I have already integrated out the fermions.
I haven't. Suppose I start with a gross level model that is a Dirac fermion coupled to the boson in the model you presented in your backup slides.
Yeah.
And it can arise from a 4 fermion interaction by doing some Hubbard Stratolovich transformation.
Yeah.
Let me fire, and let me demand that boson lives in the manifold of U8
okay. Yeah.
plus U5.
Right.
Now, if I can integrate out the fermions exactly without doing any approximation, then naively, although it seems the resulting nonlinear signal model does not have any time reversal symmetry.
Right.
But because I started with a theory that has time reversal symmetry, I think the time reversal symmetry will be hidden somewhere.
No. So the time reversal symmetry is explicitly broken. This can be shown that if you gauge the nonlinear sigma model with the electromagnetic Maxwell gauge field, it has a non-zero sigma xy.
I'm not condensing the order parameter.
Neither do I.
So I have a gapless theory using the
no. Okay. So here is the question. The question that whether in that mass manifold, say L equal to 3, you can still have the order parameter quantum disordered. That's a very interesting question.
Yeah.
Okay. Now, if the order parameter is still quantum disorder in L equal to 3, my belief is that it still breaks the time reversal symmetry, but it will restore all the U8 and charge conjugation symmetry.
So what's the order parameter that breaks the time reversal symmetry?
No, so it's the trace of Q.
But it's disordered.
No. The disorder means that the expectation value of Q is 0, of the Q matrix is 0.
Yeah.
But trace of Q is invariant under the fluctuation of Q, right?
Wait a second. I think Liu, you can think of it and let other people see whether they have a question, and maybe you can leave here for discussion later. For example, like Petri, whether other people have any comments or questions, feel free. Liu, you can stay here and then you can ask.
So can I apply the similar idea that you introduced and just for a gapless Fermi liquid, use this local U1 Goldstone boson to express the gapless Fermi liquid such that the stiffness is so that if you view this U1 Goldstone as an XY model, it's in the disorder phase.
Well,
can we apply this idea to do something like this?
Well, you know, for system which has a Fermi surface, which I believe that's what you're referring to for the Fermi liquid,
yes.
Our bosonization really doesn't work.
What's the difference in the idea?
The idea is that you really need to have a Dirac point where the low energy particle excitation is localized around one point in the momentum space.
But it seems, at least what I get from the talk, is that the main idea is to have some order parameter to gap out the fermion, but such that that order parameter fluctuates in a way that the symmetry is actually restored.
Right. Okay. That main part. Okay. Of that part of the idea, if you introduce the order parameter and gap out the Fermi surface and then fluctuate the order parameter to restore order symmetry, you know, which you wish to restore, that part is true. You can generalize it, but in that case, you know, integrating out the fermions and so on, you know, those are completely different.
Yes, the details are different, but it seems this main part.
Right. The main idea of introducing order parameter gap out fermions, then fluctuate order parameter to restore the symmetry. Yes.
Okay, and then I suppose some of those earlier questions, such as this spin structure for fermionic theories and so on, can also be asked for BCS theory, for example. And yeah, this is just a comment. Yeah.
I have a naive question. Are there any new insights or application to like pseudo gap phase?
No. I mean, no. Yeah, I mean, pseudo gap phase is really doped away. Well, we had actually spent quite a bit of time to think about doped pi flux phase, and by implementing Xiaogang's you know, SU2. So he treat the gap, he treat the doped pi flux phase, he treat the dopant as also SU2 boson. So we have spent considerable time on that subject, but yeah, but you know, we didn't reach anything worth to report. No, I definitely do not say that our story is mature enough to claim that have not anything to do with the pseudo gap phase.
Thanks. Other comments, questions, please? We'll wait for 5 seconds. If not, we will thank Dung-Hai first. Okay, let's thank Professor Dung-Hai Lee for the wonderful, patient, and passionately giving us a wonderful seminar lecture. Thank you very much.
It's a pleasure.
Yeah, people can still stay to ask questions, and the video will be online. You can, yeah.
Can I get off now?
Yeah, of course. But you mean, do you want to come back to take more questions if people ask, or whatever? You can take a break. I will leave this open and see whether some people.
Okay. I go get a cup of water and then I will come back. Okay.
Yeah. Take a break and then see whether people want to ask.
Yeah.